Thank you very much. And I'd like to, like everybody else, I'd like to thank the organizers for inviting me and for putting together such a nice meeting. I'm actually originally from Pittsburgh, so it's always a pleasure to come back. Yes, and we can joke about how the longer you're in academia, the more affiliations you accumulate. So I'm going to tell you a story today about heating and vibrations in some structures we're able to make that go all the way down to the sort of the single molecule level. First, I have to do the obligatory sales pitch for both my institution. This is our new relatively new physics building. We moved in about 5 years ago. Please encourage your talented undergraduates to apply to Rice for grad school. Please encourage your talented graduate students to apply to Rice for postdoctoral positions, and so on and so forth. We also have an interdisciplinary institute that has an applied physics graduate program that spans multiple departments, which is one reason why I've got so many affiliations. And lastly, I know Professor Hunt at CMU has been using my book. I should plug my book. I have a book that came out last year on some of this nano stuff. So I always like to start off also by acknowledging the people who really did the work. So you'll see this again at the end of the talk, and this work was paid for in part by the Welch Foundation and the Army. But the work I'm going to show you is spread out over a number of years. It was really initiated in my group by Dan Ward, who is now a staff scientist at Sandia, and it was taken over by a series of people. Yajing Li is going to be starting a postdoc with John Rogers in Illinois, or at Northwestern rather, in the summer. My former postdoc, Joe Herzog, is a faculty member at Arkansas. Mark Knight is a postdoc with Albert Pullman, actually, in the Netherlands, as you heard about Pullman's research earlier today. My current postdoc, Pavlo Zolotovin, and my current grad student, Charlotte Evans, are the ones pushing a lot of this work right now. And none of this could have been done without collaborators. Mark Knight is actually a graduate student, was at the time a grad student of Naomi Hallis, and some of the most recent stuff we've been collaborating with the theory group of Peter Nordlander and his postdoc, Alessandro Alabastri. So let me give you a little outline here of what I'm going to talk about. I will do my best to try and keep the time. Let me motivate things a little bit. So I'm going to talk about heating, which means I better define what I mean by heating. And again, as with other speakers, I'm trying to keep this in sort of the colloquium pedagogical mode for the benefit of the students in the crowd. So temperature is related to the disorganized internal energy of a system, right? We know temperature is defined through statistical mechanics and thermodynamics. And the idea of temperature is you get no net flow of energy between two systems with the same temperature. So I can have a hot thing and a cold thing. And if I join them in some way that allows them to exchange energy, what you find is that the hot thing will cool down, the cool thing will warm up, and eventually these things will reach a situation where there might be fluctuations in how much energy they contain, but there's no net transfer of energy from one to the other. So fundamentally, temperature is an equilibrium concept. That's why when you start talking about heating and driving things out of equilibrium, it always gets a little dicey exactly what you mean. Temperature is an equilibrium concept having to do with the maximization of the entropy, right? And it's defined this way so that energy flows in the direction I just said. Now, how do we actually measure the temperature of anything? Because again, this gets important if you really want to talk about heating. Well, we measure the temperature through its effects on either material properties. So you're familiar with this concept, living in Pittsburgh, right? It's just as I am living in Houston these days. You can have something like a colored liquid or mercury, and you worry about the thermal expansion coefficient of this material. And as it gets warm, the actual gross physical properties of the material change. The atomic physics folks, like Professor Zweierlein from this morning, they're a little more fortunate in the sense that with their system, they can actually take a snapshot. They can literally take a photograph of the distribution functions. Right? So coming at it from the physics point of view, when I talk about temperature, I'm really wondering about how energy is distributed in the microscopic degrees of freedom of my system. And in the atomic physics limit, you can, for certain circumstances, actually take pictures of things like the velocity distribution. OK, so what do I mean by heating? I'm going to talk basically about, a little bit at the end, if I have time, about optically driven heating. But I'm largely going to talk about electrically driven heating. So you all know the basic concept. Here is some voltage supply. I turn on a switch. And now for the young people in the audience, this thing is an incandescent light bulb. The idea here is that somehow current is going to flow, and we're going to take energy from the macroscopic voltage difference between the potentials of the battery, And eventually, it's going to end up in the microscopic vibrational and electronic degrees of freedom of the wire, and the wire is going to glow because of blackbody radiation, right? And of course, you're all familiar with the other version of this, which is just a toaster. So, like I said, heating is an interesting topic because you're somehow going from macroscopic to microscopic, and the energy sort of thermodynamically, it doesn't flow backward, right? It's macroscopically irreversible. Microscopically, you could have it flow backward. You could imagine somehow setting up the system so that everything's vibrating and wiggling around just right, that somehow you pump charge back onto the battery, but that just never happens. It's statistically incredibly unlikely, right? In the same way that it's unlikely for all the air in this room to end up in the corner. Now, we know the basic physics of what goes on here. So you've got electron-electron scattering. That's how the electrons thermalize with each other. You've got electron vibrational scattering. That's how the electrons in the lattice talk to each other. So the basic idea is pretty simple. And if you have a large number of particles and you can talk about maybe thinking about just the center of that piece of tungsten as really having some well-defined local temperature, right? It's got enough particles that you can think of it as a thermodynamic system, and you can imagine asking, gee, if I brought some other thermodynamic system into local contact with it, what temperature would that reservoir need to be for there to be no energy flow? And you could define a local temperature. Now, what motivated me to get started in this work is I've long been interested in quantum systems driven out of equilibrium, where instead of our macroscopic wire, now we've got a very small number of atoms. So now things get a little trickier, right? The same physics is basically in play. So what's going to happen here, right? Here's my little cartoon. Well, if I apply a bias, a voltage, if I apply a negative voltage to this side relative to this side, here's my gold electrode, my other gold electrode. I'm going to shift the chemical potential of the electrons on this side. They are going to start, because there's now a chemical potential gradient, they're going to start going through. Right up next to, say, my little junction area, what you can see is that the distribution of the electrons as a function of energy no longer looks thermal, right? It's complicated. Now, if I go far enough away, the electrons have had a chance to talk to each other, like 10 nanometers away. The electrons have had a chance to scatter off of each other, and they've sort of formed some locally thermal distribution here, so this thing's all smeared out because now it's hot, right? And if I go way over here somewhere, the electrons have had enough time to inelastically scatter off the phonons, and now the lattice has taken up a bunch of that energy, right? Now, I can have local vibrations as well. I can have some little molecule in my junction here, and you can imagine if my electrons have enough energy, they can dump energy into these local vibrational modes. And I thank the preceding speakers for sort of setting the stage for this really nicely. OK, so you can have local vibrations. That's fine. Now, the energy there can either flow back into the electrons or it can flow into the bulk phonons of the substrate. And so the energy somehow wends its way from the macro scale down into the microscale. And and of course, you can also get slight changes in the charge distribution as you apply a bias and so on. So the key point, one of the things that motivated me here is everyone can enumerate the physical processes at work here. But it's very, very challenging to do experiments to actually measure anything locally, right? If you can't do the experiment, then you never really know how important some of your various terms are. And there's a bunch of clever ways to try and get around this problem. There's been a lot of interest in non-equilibrium heating. You can imagine no one, I don't think, is going to be making single molecule transistors or anything for information processing. But the point is, if I imagine making a silicon device down to the 5 nanometer node, I'm going to have to worry about these same physical processes going on, right? And I'm going to worry about where my heat gets dissipated. So there's a lot of people interested in this problem. The techniques that people tend to be indirect. So you can imagine using an AFM, and there's been beautiful work at Arizona State and at Columbia. I really should add the citation for Columbia, where you yank on things and you basically with an AFM, and at high biases, things fall apart more easily. And this is some sort of a proxy for the lattice temperature. You can do Raman, that's what I'm going to talk about. You can actually put little tiny thermometers right near some small structure. Another approach to this that's particularly pretty, Pramod Reddy at the University of Michigan has made an atomic force microscope tip with a built-in thermocouple. So he can go and he can contact single molecules with a thermocouple right there. Though again, in all of these, it's tough to be really, really local. Right here, even though your thermocouple's right there, it's still 10, 20 nanometers away from where the actual junction is. And the way it talks to the junction is through phonons. So I'm interested in really local things. like I said, it's hard to get local information about the vibrational or electronic distribution functions. I'm not really going to talk about the electronic distribution today. That's kind of a separate talk. But if people are interested, I'm happy to answer questions. So let's talk about what sets the vibrations, the vibrational frequencies in the first place. If you're a physicist and you like to think about, oh, I've got balls and springs, and I can think about normal modes of some mechanical system, that's fine. But the spring constants, we all know, really come from the electronic structure, right? And this was already mentioned again in the previous talks. It's not really a perfect harmonic oscillator. There's some anharmonic spring, and the anharmonic spring is set by, you can calculate things by saying, gee, if I know where the nuclei are, I can solve the electronic structure problem, and I can basically look at how the energy of this whole system varies as I imagine moving the nuclei around, and I can watch the electrons move, and basically it's the location of the electrons that really gives me the spring constant for my bonds, right? Now what that means is if you ever want to change the vibrational frequencies, that makes it sound like we deliberately set out to do this. If in your experiment you notice that somehow you are changing the vibrational frequencies, the way you're doing that is you're somehow playing around with the charge distribution, right? And we heard in the discussion about 2D IR spectroscopy in ionic liquids, one way to do that is you could actually do charge transfer. So you can imagine, the vibrational properties of, say, an anion are going to be different than the vibrational properties of the vibrational spectrum is going to be different than for the neutral molecule. And so you can basically change how much charge is sitting on there. That's one way to really change the vibrational frequencies, and we'll talk more about that. And of course, the other approach is basically, again, it was set up so nicely by the previous speakers, is the Stark effect, right? We all know if I've got a big, puffy electron cloud and I stick this thing in a big electric field, and I'll show you how we can do that in a minute. If I stick things in a big electric field, I polarize the molecule, and that can actually, there's vibrational Stark, right? I can change where the electrons are sitting, and that changes the spring constants of my bonds. Now, the way we're measuring everything is Raman spectroscopy. Again, for the students, Raman is basically inelastic light scattering, right? So you can imagine, here's my system sitting in some ground state. I send in light, and if this is a real electronic transition, it's resonant Raman. I'm not doing that. If it's not, then it's non-resonant Raman. And if the light comes out with the same amount of energy as it went in, that's Rayleigh scattering. And it goes like frequency to the 4, and it's literally why the sky is blue. I can have a situation where the light comes out with less energy than it went in because I'm leaving behind a vibrational quantum of energy. The way you do that, the selection rules for that have to do with what the actual polarizability tensor of your molecule looks like. On a very simple classical physics level, you can argue that because the polarizability tensor depends on where your atoms sit, and if the atoms are wiggling around, you get frequency mixing between the radiation and the wiggling of the atoms. So this is called Stokes Raman if I'm basically dumping in vibrational energy. If my system's already shaking, I can do the inverse process. I can pull out vibrational energy. That's called anti-Stokes Raman scattering. All right? And as you might imagine, if I compare anti-Stokes to Stokes, I can get an idea about what fraction of the time my system is in the excited state. So this tells me something about the effective vibrational temperature. We can talk more about that in a minute. Now, one of the challenges with Raman is that the cross sections generally are really small if you're off resonance. And so how are we able to do anything if we want to look at the single molecule scale? The trick is plasmons. So plasmons, what are they? They are the normal modes of the essentially incompressible electronic fluid in a metal, right? So I can take a metal particle, and I can imagine pulling all the electrons off to one side and letting them go, and they will slosh back and forth around the ion cores. This will eventually damp out due to both radiation and the fact that this thing has some finite resistivity and the electrons all scatter. I can also have some block of stuff or some piece of stuff, and I can periodically mess up the charge density, and I can let it go, and it will also slosh back and forth at some frequency that's related to the spatial period here, right? So these are bulk plasmons, surface plasmons. And the trick is, as you can see, there's some charge separation, right? I've got excess electrons here, deficit of electrons here. The separation of charge means that under a lot of circumstances, these things can be excited by light. And the trick is that when you excite these things, the local evanescent field near these structures can be much larger than the incident field from the radiation. So if you stick something right there, it can experience a local intensity that's like g squared, okay, where g is my ratio, my gain, if you will. So if you make the right kind of metal structure, it acts like an optical antenna. Now, you really win with Raman scattering, because you don't just win because your object experiences a locally enhanced intensity. You win because your object also is sort of output coupled to the rest of the world very efficiently, right? So you can win like this enhancement factor to the 4 if it doesn't vary very much with frequency, and that's the trick. So if you can make structures where the field enhancement is about a factor of 100, then the Raman scattering rate goes up by like 10 to the 8. And we are now approaching something like the 19th anniversary of the first claims of single molecule sensitivity Raman scattering. Now we've kind of entered a renaissance of these things because, as you've probably seen in the scientific literature and in all the talks you see and seminars, there's a huge cottage industry of making novel, plasmonically interesting metal structures, right? And this is, of course, also connected to the metamaterial world as well. So one kind of structure you can make that is not exactly what we're doing, but it's related, is what's called tip-enhanced Raman. So you can basically have a pointy needle, and it can come on down, and right near a ground plane, you can have a little local plasmon resonance there. And so this is one way of getting enhancement and looking at a small number of molecules. There's some beautiful work, particularly being done at Northwestern by Rick Van Dyne on this stuff. So how do we do it? I backed into this field. I had never done any optics before I got tenure. So we were coming at things from the transport side. We were making, here's your big pads, you zoom in, and we were trying to make structures where you could stick you could break the constriction into 2 separate sides, where if you know what you're doing, you can basically make this thing a planar tunnel junction. And so it's kind of like having 2 scanning tunneling microscope tips like this, right? And we were doing a lot of electronic transport measurements, and it occurred to us, boy, maybe these things would also have nice plasmonic properties, the same way the tip-enhanced stuff does. It turns out we got very, very lucky in a number of ways. Now, I should also say, often when people talk about transport through molecules and so on, they draw cartoons that look like that. There are times when you can do this. That's probably not what we have, right? So the way we make these little junctions is we essentially, we've got a self-aligned wafer scalable process as well, but it doesn't get things quite as small. If you really want the tiniest gaps, you basically break this thing by passing a lot of current through it, and you electromigrate the metal into the tunneling regime. And you're not melting it, you're not blowing it up, but it's a tricky process. But the point is you scatter molecules all over the place, and if you're lucky, one of them ends up in between your electrodes. Obviously, this is not an industrial process, right? And that's why very often you get, you don't really know exactly what you have. The computational complexity of worrying about vibrational spectra was mentioned earlier. One of the challenges is that in principle, the Raman stuff we measure contains all sorts of information in it about how these things are sitting. If only you could do the inverse problem. It's theoretically very tough. So let me show you, and I'm getting to data very soon, let me show you what you actually do. We don't usually do large numbers of junctions in parallel anymore. But here's one of these little junctions. It's hard to see, but that's where the little break is. And we've coated the whole thing with molecules of interest. So you can throw this thing into a Raman microscope, and you can look for the Raman of the underlying silicon substrate, and that's how you figure out where you are. So there's the one gold pad, there's the other gold pad. And now you can look for the Raman emission of the molecule you care about, and what do you know? It comes from basically a diffraction-limited spot right where you made the little break. If you don't actually break this thing, you see nothing. And it's not that there isn't Raman being generated all over the place. It's just that the only place where the enhancements are big enough to see anything is in this sweet spot here. And we've got, again, we've done a bunch of work on studying this, but this is sort of setting the stage for the main point. So one thing that I'll try and take care of very quickly. So originally we thought that we had these tip modes. And if that was so, then you'd expect that the plasmon resonance would be extremely sensitive to exactly how far apart the tips are. And we had the very rare problem in experimental science. Our reproducibility was too good. Okay? We didn't understand why we got such good reproducibility about our plasmon resonances, why we were able to see stuff so often. And it turns out the trick ends up having to do, it's very cute, it has to do with hybridization. So you all know what hybridization is. Again, it's this concept of normal modes, right? I can take a harmonic oscillator and I can couple 2 of them together, and I'll end up with a some low frequency mode and some high frequency mode, right? Or I can take two 1s orbitals and I can couple them together and I will end up with a high energy antibonding orbital and a low energy bonding orbital. Well, it turns out you can take plasmons, they're just normal modes of the electronic fluid. If I couple different modes together, I get new normal modes, right? So my faculty colleague, Peter Nordlander, wrote a very highly cited science paper about this about 13 years ago. So this actually ended up solving the mystery of what are the weird plasmon modes in our system. It turns out, so if it was the tip modes, you'd expect if your light was polarized this way, that would give you the biggest signal. Bizarrely, we found we actually got the biggest signal when our light was polarized like that. It's really cute. Here's how it works. The metal strip, if it was an unbroken metal strip, it has a dipole resonance that's optically very bright, right? There's a transverse plasmon resonance in this metal strip with a big dipole moment. The field enhancements aren't very big, though. Okay? If I had perfectly squared off edges, if I had like a completely perfect interface there, there would be a bunch of higher order multipole modes that would live at that gap that would be optically dark. They would have no dipole moment. We wouldn't be able to talk to them. The fact is, in any realistic structure, you've broken all the nice symmetry, though. So what happens is the normal modes of the real structure, because of the broken symmetry, the highly localized things in here pick up a piece of this. And that's what enables the big local enhancement and at the same time coupling to the far field. So it's been very cute. My postdoc figured that out. And we were able to test it with cathodoluminescence, as was mentioned earlier, actually, this afternoon. OK, so here's what data looks like. If you sit, this was data that was taken at room temperature and air when we were first learning about this stuff. If you sit right on top of that hotspot and you record things as a function of time, you see a few things. First of all, you see that there's a bunch of fluctuations in the Raman intensity. This thing that doesn't do much, that's the Raman line of the silicon. Okay? These are the molecular Raman lines. And you notice that they spectrally diffuse. They bop around in terms of vibrational energy. And they also fluctuate in intensity. Right? That's because the local molecular environment is changing all the time stochastically in a way that we're not controlling. This can be the molecule reorienting. This can be adsorbates coming and going. Since then, we've learned a lot about trying to do measurements in vacuum at low temperatures to try and stabilize things, right? Try and make the environment that the molecule sees as constant in time as we can. So let me tell you about some where we start doing the real heating stuff. We were able to do simultaneous, this is called Surface Enhanced Raman scattering, by the way. That's the acronym. We were able to do simultaneous electronic transport and Raman in what I hope you will see, what I hope you will buy is one or two molecules. All right? So kind of a complicated setup. The point is that you're able, this is the same sort of slides I showed before. You're able to basically wire up your device and actually push current through it while you're doing the Raman measurement. Right? You need a nice optical cryostat to make this work. Here's examples of data where this is kind of the artificially nice data. Okay? I'll show you more typical data on the next slide. But the idea here is the black is the measured tunneling conductance between the two sides as a function of time. Again, we're not doing anything. This is basically, we're applying just some little tiny AC wiggle and measuring the current. Okay? So we're not trying to change anything. These are sort of stochastic fluctuations because of the changing molecular environment. So here's the tunneling conductance as a function of time. And we know tunneling depends very, very steeply on distance. So these two electrodes, their tunneling volume that's really being probed, that's dominating the conduction, is basically comparable to a molecular volume. So you see the tunneling conductance does a bunch of things. And what you find is that the Raman emission simultaneously acquired basically is extremely well correlated in time. You see a bunch of traces like this, and you become pretty convinced you're looking at Raman emission from something that's just bopping around in there. Here's a better set of data, actually. Look at this mode, and here's again the tunneling conductance. So what you find is that here's a little change in the conductance. There's a big change in the intensity of the mode. There's some big blinking event, right? Maybe the molecule goes away, or at least goes into some sort of other configuration. When it comes back, the mode has shifted and is really bright. Conductance is way up here. Mode goes back to where it was. Conductance goes back to where it was, and so on and so forth. So you see a few of these things, and you start becoming pretty convinced that you're looking at transport through the thing you're doing Raman of. Okay? Now let me get to the point about heating. I'm trying to keep an eye on the time here. So like I said, the way you're going to measure heating, the way you're going to look at heating, is you are going to look on the vibrational side. You are going to look at not just the Stokes-Raman scattering, but you're going to look at the anti-Stokes-Raman scattering as well, and you're going to compare them, right? Now, you might ask, how many anti-Stokes counts versus Stokes counts do I expect to get? Well, if you're in thermal equilibrium, you're basically dominated by a Boltzmann factor, right? There's some energy difference between the vibrationally excited state and the vibrational ground state. We never go high up in the ladder with this stuff. I should also point out, by the way, our excitation wavelength is 785, and we're doing this CW. So there's depending on how you define cross sections, there's the frequency to the 4 part, that's the Rayleigh scattering type thing. There's the Plasmon enhancement, which again, you don't really know. It's possible the anti-Stokes and Stokes processes can have different cross sections. But the thing that really ends up dominating basically is the exponential factor, right? So if you're sitting at liquid nitrogen temperature and you're looking at a relatively low energy vibrational mode, what you find is that your anti-Stokes to Stokes ratio in thermal equilibrium would be something like 10 to the minus 4. So if you got 10,000 Stokes counts, you might see 1 anti-Stokes count, right? So if your system's actually cold, that's what you got. So the big question is, if we crank up the current, does anything change, right? So same basic idea as before. Let me show you an example. So here's a junction, and this is published a few years ago now. Here's a junction involving a little oligophenylene molecule made by my faculty colleague Jim Tour. And the plots are a little different now. On the right-hand side, this is the Stokes-Raman. So here's a bunch of lines, right, Raman lines. Here's the anti-Stokes-Raman. And now the y-axis, instead of being time, it's bias voltage that I'm applying across this device, which has some non-zero conductance, okay? So zero bias, the equilibrium situation, except for the fact that I'm shining a laser on it, is here. And what you can see is, gee, at zero bias, I see nothing on the anti-Stokes side. And I crank up the bias, and I start seeing peaks appearing on the anti-Stokes side at high bias. You want to talk about electric field scales. We're applying something like half a volt across a gap that's kind of a nanometer, maybe 2 nanometers. So again, large numbers of volts per centimeter electric fields. So if you plot, basically, this is essentially a proxy for anti-Stokes counts versus bias. What you find is, if I look at particular vibrational modes, I can really seem to heat these things up by driving current. When we started doing this, I told my student, we might never be able to see anything. Because you could imagine if the molecule is really well coupled to the substrate, the electron only has some chance of dumping energy into the molecule. And if the molecule is really efficient at dissipating that energy off into the bulk, you may never be able to jack its temperature up in steady state, right? But we got lucky. Turns out you can do this. Here's an even more dramatic example. Notice this time at zero, another junction, same molecule. Notice that this time at zero bias, there's actually something here on the anti-Stokes side. It's hard to tell because of the color scales, but that's because, for whatever bizarre reason, the Stokes process is freakishly good. So we're basically optically pumping this state, this vibrational state. And the way you can tell, actually, is that the Stokes intensity scales like the incident intensity linearly, and the anti-Stokes here scales like the incident intensity quadratically. The data is in the paper, actually. But the point is, so look at this one. Again, at high bias, things start happening. And this is really cool, right? So here's that mode. And as I crank up the bias, nothing happens, nothing happens, nothing happens, nothing happens. And at some point, there's a threshold where suddenly it starts getting vibrationally more excited. What is that threshold? It's right when the bias, E times V, equals that vibrational energy. Right as soon as the electrons, in principle, have enough energy that they could kick the vibrational state, they do it. Right? So this has been very fun, very, very fun to study. Now, I'll skip talking about electronic heating. Let me say something, some more recent results. So one thing we noticed when we were doing these experiments was, so it's particularly clear, by the way, in recent stuff we've been playing around with C60. C60 is a great molecule and a terrible molecule. So it's great because it's been very well studied. Quantum chemistry people can do all kinds of things with it. One reason it's terrible is it's got crazy high symmetry. So it's got a whole bunch of high symmetry modes that are all 5-fold vibrationally degenerate. And as you can see, they're horribly complicated to look at. It's very hard to glance at one of these modes and be like, well, of course, that's exactly what's going on. And also, when you put this molecule on our surface, you lift that five-fold degeneracy, right? So you end up with a whole bunch of peaks that are hard to interpret. But what's pretty cute is, we were studying this stuff and we found, again, here's the heating, right? Here's the anti-Stokes side. At low bias, not much is going on. And at high bias, you get a lot of anti-Stokes intensity. And you'll see on the next slide, here it is again. You can really look and track individual modes and say, gee, when does the anti-Stokes stuff really turn on? And it's basically when the bias equals that vibrational energy, right? So you can really look at inelastic pumping of vibrations by current. Now, going back here for a second, if you look at this, you notice these lines are not flat. They're curved. They're all concave down, or at least a lot of them are. We were surprised by this. We tried to look at, and we'd actually seen something like this a little bit on those oligophenylene vinylines where my student would, in fact, the reason this looks so ugly, this was my student Dan hitting the up arrow key and the down arrow key on the computer, right? So this was not a programmed waveform in any way. But you could see, boy, some vibrational mode was moving around as a function of the bias in some systematic way. And in the case of the C60, it's really quite clear. You can zoom in with a higher resolution grading and play with the color scales. Things are really curved, right? There's some funny business where at high biases or at high electric fields, the modes get softer systematically by not terribly small amounts, 10 wave numbers, 15 wave numbers in some cases. And so here's a particularly a big example. You can see there's a glitch in the middle, one of these reconfigurations of the junction things in the middle of it. But you can really see these curvatures. So our first thought was, hey, Stark physics. We know some quantum chemists. We can say, do me a favor, calculate the vibrational spectrum of C60 in a DC field. And they said, oh, we can do that. So we were working with Jeff Neaton, who's currently the director of the Molecular Foundry, actually, at LBL, and Leor Kronik, who's at the Weizmann Institute. Peter was Jeff's student. And we said, can you do this? And they said, well, we got good news and bad news. The good news is, yeah, we can do it. We can just impose an electric field in our calculations. The bad news is it doesn't really do much. The modes don't hardly shift at all in the neutral C60. And when they do shift, they don't shift systematically. Some go up, some go down. And if you take C60 minus, which the C60 on gold can grab an electron, or it can grab some piece of an electron, the effects are a bit bigger, but again, it's not systematic. But they pointed out what might be going on. It turns out if you could dial around the amount of electron on the C60, then things start happening. Because C60 minus really actually does have a rather different vibrational spectrum than C60 neutral, right? So what's the idea here? The idea here is, here's what one of these modes looks like. And as a function of how much charge you put on the molecule, you can change where this mode sits. And it turns out you don't need to change the charge by very much to get what we see, right? And you can come up with a very simple model, like an analytic model, where you just say, I've got some Lorentzian, my lowest unoccupied molecular orbital is some Lorentzian with some broadening, and it lives up here somewhere. And you can just say, gee, if I crank up the voltage, I start picking up more of the tail of the Lorentzian. I never get all the way to resonant tunneling, but I pick up more of the tail. And you can just run the numbers, and it basically works. So this is a simple toy theoretical calculation a little bit. And with very sensible numbers, you get curvatures, particularly of the high symmetry five-fold degenerate modes that are very similar to what we see in the experiment. Okay? Now, I should point out, boy, if we could gate this, if we could electrochemically go through a redox transition, all kinds of crazy stuff should happen. We have been trying this. It turns out it's extremely difficult. Not entirely clear to me exactly why it's as hard as it's proven to be, but we're still trying it. I should also point out, by the way, besides charge transfer, something else that happens is when you really truly model the full junction, you got the metal in there, and it can do dynamical screening processes as well. So our toy model didn't account for that, but Abe Nitzen, who is now at the University of Pennsylvania, he'd been at Tel Aviv, worked with some folks, and the effects are very similar. Now, more recently, we said, gee, well, if what we were seeing wasn't Stark physics, can you ever see the vibrational Stark effect? There are plenty of people who claim that they use it all the time, and we've got big electric fields. And so what we did was we started working with PCBM, which is a derivative of C60 that the organic photovoltaic people in the crowd are all familiar with. So it's got a permanent dipole moment, right? So here's examples of very similar looking data that you take with PCBM, and I want to point out a couple of things. See that mode where it shifts very linearly with field? And this one where it's curved, but there's a real slant to it. And there's even more dramatic ones. See, there's real tiltiness to it, right? You basically see these in PCBM devices, but not nearly as much in C60 devices. This is one of these, again, for the students in the crowd, this is one of these weird, frustrating things where your eye is really good at picking this out. And if you then want to actually come up with a statistic to truly demonstrate it mathematically, it's hard. The reason it's hard is because if you want to basically ask a computer to identify where all the modes are and track them, there's just a little bit of noise in there in trying to do that. So there's sort of a floor, right, about how well you can really determine anything. What we did was we basically said, my student, Jenny, said, well, OK, let's look at some mode shift away from zero bias and have a linear term and a quadratic piece. We can basically track these things with the computer, try and fit this to a quadratic fit, right? And what we're going to do is we're going to histogram these P1 and P2 values for C60 and for PCBM. So what you find for C60 is, yeah, that linear piece, it just kind of bops around a few inverse centimeters per volt, okay? And so here's the distribution for C60 for a whole bunch of modes and a whole bunch of junctions. And if you do the same analysis for PCBM, you get something with a much fatter tail. Now, this is a little bit of a cheat because there was one that was crazy extreme. But the point is that you really do get a much bigger tail. And similarly, actually, if you look at the quadratic part, if you look at that P2 coefficient, here it is for C60, where, again, you can get some big curvatures. And for PCBM, you actually get a little bit less curvature. But there really are systematic differences in studies between the two different molecules. 3 minutes. OK. Right. So it turns out our theory colleagues can basically do the same sort of calculation, right? They can try and do the quantum chemistry calculation for PCBM. They can try and factor in this Lorentzian level business. And again, admittedly, it's a toy model. It's not truly doing the DFT problem, including the metal and the full junction and everything. But what they find actually in the theory is, and this has just been published recently in Nanoletters, they actually get the same kind of systematics. Right? They really see there's a lot more linear shifting going on in PCBM. The one thing that's interesting, the calculations don't show, well, the linear terms that they find in the calculations are too small by about a factor of 5 from what we actually see in the experiment. And we have reasons to believe, we explain this in the paper, it's because they're not really modeling the junction. We think there are image charge effects and other things that come about in the real junction that basically make this effect bigger. All right. In the last minute and a half, I will basically just tease something. I only have a couple of slides on it. We've also worried, you might wonder, you're shining a laser on this thing. How cold does it really get, right? So we've actually studied that. And you can actually do some cute things. You don't even need a junction. You can just make a constriction. And you can use the resistivity of the metal as a thermometer. So you can just shine the laser on there, right? And you can rotate the polarization, and you can see how much the resistance of this thing, you can chop the light, and you can see how much the resistance of the thing changes by having light on there. And you can essentially do thermometry. So the bottom line is, and you can also see the plasmon resonance as opposed to direct absorption. If the polarization is like this, you see the transverse plasmon. If the polarization is like this, you don't. You just get direct absorption in the metal. So you can actually quantify these things. You can play games with the substrate. You can play games with being on resonance or off resonance in different ways. So this has all been done too. And my postdoc actually has a paper that where this is in submission basically. It's quite interesting. We've extended this to lower temperatures. So here's the bottom line. If you sit at basically 100 Kelvin and you shine the laser on there and you put kind of a couple of milliwatts in your 1.5 micron diameter spot on this thing, you heat the temperature from like 100 Kelvin, you heat the temperature of the metal from 100 Kelvin to like 102 Kelvin. If you put the substrate at 5 Kelvin and you shine the laser on there, you heat it from 5 Kelvin to 90 Kelvin. Okay? this is a problem, right? If you really want to do low temperature things. And it's actually not linear in the incident power for reasons that we understand. The thing that ends up actually killing you is there's a thermal boundary resistance, an acoustic boundary resistance between the metal and the dielectric substrate. So and that basically makes the heat transfer much worse as you get colder. It goes like 1 over T cubed. So you really run into problems trying to get things very, very cold. And we've got some interesting stuff in the pipeline working on this, and I'll be happy to answer questions about it. So let me just conclude. You can play all kinds of cool games with plasmonically active structures, and this lets you do neat things. You can use Raman spectroscopy, for example, in conjunction with transport to learn about what's going on in non-equilibrium quantum systems. And basically, there's a whole lot of complicated physics and chemistry that goes on in these systems, and there's a lot left to do. So I'll just leave this up, and I'd be happy to take questions. Thank you very much for your attention.